How are you feeling, Professor?
I'm better. Keep my finger crossed.
I'm glad you're feeling a little better.
Yeah. I still have a lot of tests and exams and scan and all the stuff, but you know, I hope. But I think I can go back to teaching unless another infection hit me and back to bed. Thanks for asking, Rachel.
Of course.
I've been teaching for like, I don't know, 25 years. That's the first time ever I had this issue. I basically never almost missed a class. So this was weird.
Yeah, I knew you definitely weren't feeling well if you were missing class.
Yeah, it's just like, I've never had that before. Yeah, I was having 104 fever, so it was big deal. Anyway, how did it go with induction, guys? Any comments? All right, I have a homework about induction. I put it on Brightspace like an hour ago. It will be due next Tuesday. So you guys work on it. And if you have like any questions, any issues, so you just email me and I can like meet with you through Zoom or any other, through Zoom, basically. I can arrange time, meet with you through Zoom so I can answer your questions in case you had difficulties with them. Okay, so don't shy away from, telling, I have my office hours that you can show up. And if you're struggling, ask for a meeting and I'll arrange a Zoom meeting with you for induction because it's a very important topic. All right. Okay, so I'm going to assume that induction is over with until you guys tell me that you have questions about it, and then I will work with you on it. And today I'm going to go back to pick up where I left. I chose the topic induction for Professor Tarfulaya because it's independent from the other stuff. I didn't want him to get in the middle of something. So today we are going to do like a couple more problems that has to deal with contradiction. And then after that, I will start proofs involving set. Okay, so that's really the plan. And when we're done with this, I still have, of course, we have functions. We're gonna learn about them. So today I will pick up a couple of more problems about contradiction, and then I will move on to a proof involving set. So as an opening, just to get us back into the mood, let me take a small problem. So remember, contradiction, it means we assume that we're working with is false. We try to, get to a place where I say, okay, if I assume it's false, I ended up with a nonsensical statement. So there is a contradiction. So my assumption is actually false. It means my original statement is true. So let us just as an opening, show something simple. Suppose I tell you prove that there are no positive integers So there are no positive integer solution. It means, I will explain what does this mean, to the equation x squared, let us say, minus y squared equal to 2. Okay? So my question is, there is no way you can find positive integer solution. It means you cannot find x and y, which are integers, and which are positive, something simple, that satisfy this equation. Okay? So, okay, there are no positive solutions. We're going to do it by contradiction. So what does it mean? What does it mean do it by contradiction? It means what I'm going to assume. Just speak up. You don't have to chat. Just speak up. What shall I assume? Okay, that's a statement. There are no positive solutions. I want to prove it by contradiction. It means what shall I assume to do it by contradiction?
Assume there is a positive integer.
We assume there are positive integers and 2. So we can assume that I can find x and y in Z plus, because I want them to be positive, such that there is a solution. So such that this is satisfied. Okay, and now we're going to show that this is really lead to a contradiction. This is really get me to a nonsensical statement. All right, so what shall I do? So that's my assumption. How can I go from there? So ideas? So what shall I go? Anyone? What jumped your eyes here? What jumped your eyes when you see that? Okay. All right, and then what do you want to go from there? Let me make it a little bit simple. X squared minus y squared. This is, yeah.
X plus y multiplied by x minus y.
Very good. I mean, yeah. Means that this is equal to 2. Okay, so I just really try to analyze it. And now remember that I'm dealing with integers. So if this product is 2, what can I get from there? What does it mean? How can this occur? How can this occur? Shah, can you keep going? I think I'm pronouncing your name correct.
Are you talking with me?
Yeah, I'm talking to you. Yeah, how would you want me to address your name?
You can say Kai.
Hi, here we are. What do you want me to do from here?
So
you have two numbers, integers. When you multiply them, you get a 2. How can this occur?
So only possible for here is 1 multiplied by 2.
Right?
Yeah.
But
So I have no idea.
that's okay. These are two integers. This one is an integer and this one is an integer. If their product is 2, how can this occur? If one of them is 1, the other is 2, because 2 is prime. You cannot split it into two integers unless one is 1, the other one is 2. That's a possibility. Or you can take x plus y is 2 and x minus 1 is 1. This makes sense? So the only way that's to occur if either this is 1, this is 2, or this is 2 and this is 1. And because they are positive, I cannot take x plus y equal minus 1 because I know that my number positive. You can do that. Yeah, you can do that. We don't have to, but we can do that. You're right. Yes, we can. So now, if this scenario occurs, what does this tell me? If those are two equations, suppose this is the scenario, plus y minus y cancel each other out. I will have 2x equal to 3. It means x equal to 3/2. That's a contradiction. This is not in Z. So if this occurs, my x will not be in Z. So that's really contradict. That's a false statement. So this is a false statement. Now, in this case, plus y minus y, also 0. Also, I'm getting 2x equal to 3, x equal 3/2. And that's a contradiction because this x is in Z, but this is not in Z. This is in Z, and this term is not in Z. So we're getting a So we have an integer equal to a non-integer. That's my false statement. This is false. It means assumption is correct. Assumption is false. But what is my assumption? My assumption is I can find integers. My assumption is false. It means given any x, y in Z plus, x squared minus y squared is definitely different from 2. Okay, so that's idea of a proof by contradiction. Okay, please ask questions as you move on. So the other problem we're going to do by contradiction also is the problem I promised you. I will show it to you, which is the fact that the square root of 2 is irrational. Okay, so that's a very classical proof that you should be definitely aware of it. Any questions before we proceed? Right. So square root of 2 is irrational. Now, before we talk a little bit about how can we prove square root of 2 is irrational, let me tell you a little bit, for 1 minute, a history of that. Historically, it means during the Greek times and stuff, people thought that the only numbers in existence are the natural numbers, because they can count things. So those make sense to them. And the other set of numbers are rational numbers, because this makes sense to them. So if you have two objects and they are comparing them to each other, so they say, okay, this is 2/3 of that. So the 2/3 made sense to them intuitively. So everything like this, 5/2, so the rational function historically made sense to people. When I say historically, I'm talking about 3000, 2000 BC. So during Pythagorean and stuff like that. So they thought that the only number in existence are those, the natural numbers, because we count things, 2 sheep, 3 sheep, and so on, and fraction, if you want, or rational, because they help us to compare. This is 2/3 of that. This is 1/2 of that. This is 5/2 of that. It makes sense to them. Then Pythagorean group came with the famous Pythagorean theorem. Okay, and suppose I take an isosceles triangle. This is a 1, and this is a 1. So Pythagorean theorem told them, because they proved it, that the length of the side satisfy, so c squared is equal to 2. And they spent a lot of time trying to find the c. What is the c that satisfies c squared equal to 2? It exists. That's the length of this line segment. They knew that. But their question is, what's the c? And they only understood those numbers. So they tried every possible rational they can think of, and they could not find any rational. When you square it, you get 2. And this was the beginning, where people start thinking that there are numbers that cannot be written like that. And it was a big dilemma for them, because they could not understand irrational, which are not easy. So when they were faced with this dilemma, then they start asking themselves, is it possible to write as irrational? And they came up with the proof that we're going to talk about it right now, that actually it's impossible to find a rational number when you square it equal to 2. But the whole idea started actually from Pythagorean. That's where they were faced with this question. Can I find a number when you square it equal to 2? And they really struggled with that. Till they found that they can't, and they used the proof by contradiction, which is the proof we're going to talk about right now. So it's a really old proof, so it's not really nothing new about it. So that's the idea of the square root of 2, and that's where the beginning of the idea of irrational numbers. So let us going to show the following. And that's the first proof, that square root of 2 is irrational. It means I cannot write it as P over Q. That's really what it means. So we're going to prove by contradiction. So by contradiction, it means assume this. That's what contradiction is. We're going to assume square root of 2 is rational. And somehow I have to convince you that this will lead me to something wrong. Okay, so what does it mean, square root of rational? So assume that square root of 2 can be written as a p over q, where p is an integer, q is an integer, but I want to make one more assumption on p and q. Suppose this has happened, where p and q has no common factor. Does this make sense? Where, of course, PQ in Z, Q non-zero, and PQ have no common factor. Can I make this assumption? Yes or no? Can I make this assumption?
Yes.
Because?
Because it's rational and you just make it's fair.
Because if they have common factor, what can I do with them?
It's just common factor.
Right. Suppose it's 4 over 6. I can basically, they have a common factor of 2. This is the same thing as 2 over 3. It means I can write them in their lowest form. So my assumption is fair because if they have common factor, I get rid of them. And I write them so that there is no common factor between them. So it's a very fair assumption that we can justify. All right, so now, of course, I want to get rid of the square root of 2. I'm going to square both sides. So if I square both sides, I get this, or square both sides. Square both sides. And, okay, then this will give me p squared over q squared. Okay, so now I'm going to multiply, and that's the original proof. So this will give me that p squared, I'm going to cross multiply, is 2 times q squared. Okay, now this tells me that p squared is even. Right? It's 2 times an integer, it's even. Now, we proved before in class, we showed the following, that if p squared is even, then p is even. And we did that by contrapositive. That was my first proof by contrapositive, because we said if p is odd, p squared will be odd. So if p squared is even, then p will have to be even. So what does this mean now? It means that p can be written as 2k, where k in z. Okay, now I'm going to substitute p back into this. So substitute 2k for p. Then we get 4k squared equal 2k squared. Okay, so imagine people were able to do those kind of proofs, thousands of years before BC. I'm going to have now divide by 2 across. I will get 2k squared equal to q squared. Okay. All right, anybody see anything? I'll give you a minute to interact a little bit with what was happening.
Since the p is even and the q is even, so they have the common factor too. So that is not
right.
what
This will go ahead. This will contradict what?
P and Q have no common factor.
Exactly. Okay, so no, I'm not going to do it forever. I'm done, almost. So now 2k squared equal q squared. This will give me that q squared, because 2 times integer is even. So this means, again, that q even. So now we have the following. Now we have the following. P is even and Q is even. So if I do this assumption, I will end up with P and Q is even. It means that P and Q has a common factor of 2. Have common factor of 2. Okay. And that's contradict our assumption that P and Q, but this contradict our assumption. So we assume that P and Q have a common factor, don't have a common factor. But if we assume square root of 2 is rational, then P and Q will have a common factor. So that contradict the assumption, the fact that P and Q has no common factor. No common factor. So if
You
we
want to put
assume,
that up a little?
oh, here we are. That's it.
Thank you. Yeah.
So if we assume the square root of 2 is irrational, then we end up with a false statement, because we end up with a statement that tells me P and Q have common factor and P and Q have no common factor. Hence my original assumption. So the original assumption is false. And the square root of 2 is irrational. Okay? And actually we can imitate this proof somehow and show that square root of 3 is irrational. We can show that the square root of every prime number is irrational, and we can show a lot of numbers are irrational using kind of a similar approach. Okay? So that's my first number that I show you for real why it is irrational. Now, are there a lot of, can you do this? Will you become a factor always be the prime number? Yeah. Mm-hmm. Yes. Now, how many irrational numbers are there? And this is really kind of interesting. If we have time, I don't know if we will, but I can talk more about that at the end of the semester. But now we know that the square root of 2 is irrational, right? That's, I hope I convinced you with that. I didn't. I mean, that's the proof is very classical one. In class, we showed the following. If you take any rational number and you take a rational and you add it to an irrational, then this is again irrational. And that's proof done in class. Okay, so are there more irrational? Oh, there are way more irrational than rational. And now let us build how many irrational, only with those two facts. How many irrational can we have? Every time A is rational, you add to it the square root of 2, you get irrational. So that's the minimum. I'm only using the fact that this is irrational. Let us build. So square root of 2 is irrational. 1 plus the square root of 2 irrational. 2 plus square root of 2 irrational. 3 plus square root of 2 irrational. Because rational plus irrational give me irrational. And then I can have more. A half plus square root of 2. 3 half plus square root of 2. 5 halves. And then I can take a third. So you can see how much irrational I can build only from one irrational numbers. And one of the actually very, very nice fact is that there are way more irrational than rational function. And that is the concept of countable. We can show that the rational number, even though it's beyond us, can be listed. So they are infinite, but we can somehow list them. We can put them as a list. Irrational cannot be listed. And we're gonna call the irrational, they will be called incountable. It means we cannot write them as a list. However, the rational number, they will be called what's called countable. It means we actually can put them in a list. If I have the chance at the last hour of the course, I will come back to this idea. But the bottom line that there are lots of irrational number, way, 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 way more than rational. Okay. Isn't countable correspondence to like the, yeah, the countable is the cardinality of the integers, and we actually can show that the rational numbers have the same cardinality, quote unquote, as the integers. It's a very fun proof, but we can also show that. However, I cannot show that the irrational, they are not, have the same cardinality as the integers. Okay. All right. Now three just true or false questions. Very simple. Okay, true or false question. Irrational plus irrational is irrational. True or false? Means if I take an irrational number, I add to it an irrational, will I end up with an irrational? True, justify, false, justify. So what we know is rational plus irrational give me irrational. This we proved it in class, and make sure you know the proof of this simple fact. Okay, we did it by contradiction. Assume rational plus irrational is rational, and we show that this will have to be rational. That's okay. Now, is irrational plus irrational irrational? I'm having two different answers. If you tell me false, I need an example. So if Peter said false, I want an example. Use square root of 2 for now. False an example. It means give me one irrational, another one, add them. I want an irrational. Now, your example doesn't work. No, because if I take square root of 2 plus 1 over square root of 2, I will get 2 plus 1 over square root of 2. I will get 3 over square root of 2, and that's an irrational number. Okay, who can give me an easy example?
Could you do root 2 minus root 2 equals 0?
Right. Root 2 minus root 2. That's an irrational. You can say this is plus minus that. And that's irrational. 0, which is rational. So we have to be a little bit careful with those. Yeah, now it works. Okay, along the same line. What about irrational times irrational? Times an irrational. Irrational times irrational. Is this irrational? Yeah. Okay, true and false, quick. Anyone? Okay, I have one, which work. It's false. Okay. Example. Now, one of your classmates is using the fact that E is irrational, which is absolutely correct. Okay, that's not an easy proof that E is irrational. And so I will not use E. I will use the very simple one. Take square root of 2, irrational. And okay, I can multiply it by 1 over square root of 2, which also we can show that is irrational by the same technique. So that's equal to 1. Irrational, irrational is not irrational. So we have to be careful when we work with those ideas. So what we have is rational plus irrational. Give me irrational. So that's what we have. Rational plus irrational. Give me irrational. And rational times irrational. Give me irrational. However, if I multiply 2 irrational, anything can happen. If I add 2 irrational, anything can happen. Okay. Right. The last thing we're gonna do before I move to back to sets.
You can go back to that. Sure.
Okay.
Mhm.
Right. So now the last thing we're gonna mention is the idea of a biconditional statement. So biconditional statement. Okay. Or if and only if statement. So some statement in math will be like this. So we talked about that when we talked about logic, but I will talk about that again. Suppose you have a statement like this: given any x in D, P of x, we have a predicate, whatever P of x is, if and only if Q of x. Q of x. Okay, so P of x, so what does it mean? This is true. What does it mean for a statement if and only if is true? It means that this true if for all x in D, if P then Q is true and the converse is true. So if P then Q is true, so that's what if and only if mean. And the converse of it. What does it mean, the converse? And for all x in D, if Q, then P is true. So if and only if statement is true means whenever P is true, Q is true. And whenever Q is true, then P is true. That's what if and only if statement in math. So if I want to prove if and only if statement, I actually need to prove two things. I have to prove if P is true, Q is true. And if Q is true, then P is true. So that's what the biconditional statement. So let me take a very straightforward example. Suppose. So example. Let n be an integer. Show that n is odd if and only if and only if 3n plus 2 is odd. Okay. So whenever we have a if and only if statement, whenever we have that, means we need two proofs. Okay, so we have to prove two things here. We have to prove first. I'm gonna do it like this. So it means we have to prove if n is odd, then 3n plus 2 is odd. And we have to prove if, means if this is true, then this is true. And if this is true, then the other one is true. And we have to prove if 3n plus 2 is odd, then n is odd. So that's what it means if and only if statement. It means they have the same truth value, that they go together. Okay. Or P of x is equivalent to Q of x, anything you want. So let us prove this, and this is easy. So if this is odd, then this is odd. So direct proof is definitely the way to go. Direct. I will do that quickly because this should be easy. So assume n odd. And I have to leave to go to 3n plus 2 odd. All right. And odd, it means n could be equal, mean there exists a k in z, such that n equal to k plus 1. But that's what I am eyeing, the 3n plus 2. So I just take 3n plus 2 equal 3 to k plus 1 plus 2. It means 6k plus 3 plus 2. Now I have to write this as a odd number. So I need to split the 5 into 4 and 1, basically. So I can write as a naught. So I will have 6k plus 4 plus 1. And I factor out my 2. I will have 3k plus 2. Okay. Now I know that this is an integer. So this is going to be written as 2j plus 1. J is in Z. It means 3n plus 2 odd. Okay. Now, how about the other one? How do you want me to do it? If 3n plus 2 is odd, then n is odd. Which approach you like me to do? You want me to do direct? You want me to do
Wouldn't you do contra? Yeah, contra. I would say
positive?
positive.
Right, contrapositive is the best way to go. All right, because direct is hard. If 3n plus 2 is odd, it's hard to get to n from 3n plus 2. So we'll do proof by contrapositive. Okay, it means we assume n even. And my goal is 3n plus 2 even. So that's really what I'm aiming for. Okay, and this is easy. Assume n is even. It means I can write it as a 2 times an integer. Okay, and now I substitute it back into 3n plus 2 because that's really what I care about. Plus 2. Now, of course, I have the 2 in here and the 2 in here that I can factor out. It would leave me with 3k plus 1. That's an integer. I will write it to be my j. So that's equal to 2j, j in z. It means 3n plus 2 is e. So that's really the if and only if statement. It means the two statements have the same truth value. They are really equivalent to one another. I can do this problem by contrapositive and I can do by contradiction. Usually when I can do it easily by contrapositive, I don't really go to contradiction. I would rather do it contrapositive because it's more direct. Right? So whenever in math, and this is you will encounter a lot, you know, in math there are a lot of theorems and you guys will see them. And the theorem will tell you if and only if. And it's crucial to understand what do they mean by if and only if. So the only simple math theorem, are you guys done? Okay, like a simple math theorem that probably some of you remember because most of you have done linear algebra. Suppose I tell you, okay, let A be a n by n matrix. Then A is invertible if and only if, and that's how the statement will come up. If and only if the determinant of A is different from 0. Okay, typical statement in linear algebra. All right, so what does this mean to you now? It means that if you take a matrix and you know that you can invert it, then immediately you know that the determinant is not 0. Now, if you take a matrix and you compute its determinant and you realize that's a non-zero number, then immediately you can say that I can invert the matrix. So it means those and those have the same truth value. If this hold, this hold. If this one hold, this one hold. So if and only if, a very strong statement when you have it in a theorem. Okay. All right, now we're going to do proofs, but they involve sets. So how to really work a little bit with set. It's a bit abstract, but it's a crucial part of learning how to write math. So it's chapter 11, my memory in your book. It's proofs involving sets. So at the beginning of the semester, we worked with set using Venn diagram and stuff like that. Now we're going to be a little bit more precise. So proofs involving sets. Now, before I do that, I have to remind you the basic operation on sets, because now they are important for us. So basic operation on sets. On sets. So we have a universe and A, B, C. I don't know if I need C. No, I don't think so. A, B subset of a universal set U. Okay, so let us remember the basic operation. First, A union B. So A union B is defined to be all x's such that x is in A or x is in B. Okay. Now we need those definitions in a very precise way. A intersect B, all the x's which are in A and in B. Then A minus B, the difference. All the x's in the universe which are in A but not in B. That's the difference. Then we have the complement. The minute I say complement, I need a universe. Without universe, I don't have the complement, because the complement is what's not in A. So if it's not in A, it has to be somewhere. So where is the where? Is the universe that we set up at the beginning. So the complement is all the x's in the universe which are not in A. Okay. Then, so it has basic operation. Then A cross B, the Cartesian product. It's all the ordered pair, xy or AB, whatever, where x is in A and y is in B. And the final thing we saw, the power set, all the subset of A, all the x's, that's that x is a subset of A. So these are the basic operations that we talked about at the beginning of the semester, and we worked quite a bit with them in a computational way, that these are the basic operations on set. All right, today what we're going to start learning is how to prove that a set is a subset of another set. Okay, so at the beginning of the semester, I basically gave you, okay, use the Venn diagram to check whether something like that are equal or not equal. So those equalities. Right? I did that using Venn diagram. Now, in this today and next time, we're going to start proving those algebraically. How to actually prove that this is actually equal to that and this is equal to that. So we did them using the Venn diagram, but Venn diagram is finally a picture. And we have now to learn how to do those kind of things purely in an algebraic way. So let us recall, what does it mean to say A is a subset of B? So how to prove in general. So let A be to subset. How to prove that a set A is a subset of a set B. So I have two sets. How to show that this means? Let's go back to the definition. What does it mean to say that A is a subset of B? So let us recall. A is a subset of B means what? Who can finish my sentence? What does it mean to say that A is a subset of B? So that's really the picture. That's A is a subset of B. What does it mean? in terms of element. In terms of element.
A is in B?
No, yeah, what does it mean to us? Now I want to rewrite the sentence using elements. Okay. Suppose I take the following set. Let A be all the integer x in Z such that 4 divide x. Okay, so it means all the x in Z such that, so it means what are the x's? Let's make even Z plus. 4 divide x, it means this stuff, right? 12, 16. And let me take B. You don't have to write, just listen a little bit. Such that 2 divide x. It means, and Z plus. So that's 2, 4, 6, and so on. And my simple question to you is A a subset of B?
Yes,
Because,
because every element in A appears in B.
exactly, that's what I want. Why is a subset of B? Because every element in A is an element in B. 4 is in B. 8 is in B. Because intuitively, if 4 divide x, it means if x is 4 times something, x is going to be 2 times something. So is A inside B? Your answer is yes, because every element in A is in B. Now, is B inside A?
No,
No, because
because elements in B do not appear in A.
not, yeah.
There are elements in
There
B
are,
that
it's
do not-
crucial.
yeah.
There are elements, it's important because I can find an element in B, let's 2, for example, which is not in A. So this doesn't hold. So what does it mean, A inside B? Okay, A inside B means every element in A is an element in B. That's what it means, A inside B. So now let me rewrite it. A inside me mean that if X is an element in A, then X is an element in B. So that's really what it means. A is a subset of B. It means if you take any X in the universe, if this X is in here, then it is in here. That's what it means. A is inside B. Every element in A is in B. That's really what's happening here. Everyone is in here. Everyone is in here. Everyone is in here. So to prove, now, to prove A is a subset of B, we're going to do like a direct proof. What does it mean? It means we start with an element. It's an if-then statement. So A inside B is really becoming an if-then statement. So to prove A inside B, we prove the following. Given any element, if this element is in A, we're going to do direct proof, then this element is in B. So to prove A inside B, we proceed as follows. We say, let X be an element in A. So, and we prove or we show that X must be an element in B. So it's basically, we're doing a direct proof in the following sense. A inside B means if X is in here, then X is in here. So how can I prove that? It means I prove the following. If I start with any element in A, so let X be in A. So if you take an element, let's find my hypothesis. My hypothesis X is in A. And I show that this element will have to be in B. So that's how we prove a set is a subset of another set. Now, I'll take first a very numerical problem, and then I'll move to the more abstract problem. So I'll start a numerical, very simple, just to make sure you understand the concept, and then I will do more abstract idea. So suppose I take that. Very like the problem I gave you a minute ago. Show that the following set, that, let me say, 18 divide A is a subset of all the element A in Z, such that 6 divide A. Okay. So for me, this is a set. That's my A. And this is a set. That's my B. Okay. I want to show that A is a subset of B, right? By using this approach. So how do we do that? We take an element in here, and I have to show you that this element is also in here. So we start with an element in A. And now my goal right here, my goal here is to show that this element has to be in B. If it is in here, it's forced to be in B. Okay, but this is not very hard. Let X be in A. That's a numerical one. What does it mean? It means that 18 divide X. That's the definition of A. Okay, and I know that that's where I go. So I never lose track of what B is. So it means that I can find an integer K in Z such that X is equal 18 times K. I want to show X is in B. Means what I want to show, so I will write it here for me, means I wanted to show that if it's in B, it means 6 divided. Means I want to show that it's 6 times an integer. That's really what I want to show. That's really my goal. But I can get that very clearly from here. So it means X could be written as 6 times 3K. So I can put J to be 3K. So X equal 6J, where J is in Z. It means 6 divide X. So X is in B or belong to B by definition of B. Okay, so that's how we write. We show that a set is a subset of another set. This is numerical, not really an abstract one, that the one we're going to be doing in a second, but that's the idea. I want to show this is a subset of that. I pick an element in here, and this element will have properties. Of course, it's not, you have something. And I show if it is in here, then it must be in the other one. So that's how we prove inequality. Okay. Now we're going to take, as I said, a slightly more abstract, simple fact, but we're going to show them using, those ideas I'm trying to develop. So we're going to prove all the properties of set, but we're going to prove them algebraically. So let us see the following problem. So we have A, B, and C. I don't know if I will need C, subset of a universal set U. Okay, so that's really my, I want you to, we're going to prove the following. Prove that A intersect B is a subset, let us say, of A. Is this a true fact? Intuitively, just look at it. Is A intersect B is a subset of A? Yes or no? Quickly.
Yes.
Obviously, yes. I mean, this is my A, this is my B. That's the intersection. It's of course subset of A. But now we're going to prove it. And let's see, that's a simple one, but it will teach us how to prove. How to prove this is a subset of that. All right. We start with an element in here. We say let X be an element in A intersect B. We start here. And then you have to convince me that X is in A using definition, logic, anything. So that's how, so here at the end, you have to tell me, hence X is in A. That's what I expect. So now let X be in A intersect B. What does it mean? Let's intersect B means that X is in A and X is in B. This is by the definition of intersection. Okay. So it means my X is in A and my X is in B. So it means this statement is true. Now, that's an AND statement. If this is true, means in particular, it means both of them are true. So it means in particular, X is an element of A. Okay, trivial proof, but that's set the stage for what we're going to be doing. So A intersect B subset of A, you start with an element in here. You want to tell me that it has to be in here. Then you say, okay, if it's intersect B, by definition of intersection, it's in A and it is in B. It's in both of them. But the one I care about is in A, so in particular, X is in A, and of the proof. Okay? Now, let's prove another simple fact. Show that A is a subset, basically, of A union anything. Okay? It means if you take A union anything, A is a subset of it. Now, logically, of course, it makes sense, because if this is A and B, this is the union. Of course, A is a subset of A union B. Now, let us see how do we prove that. Okay. We start with an element in here, and we say, let X be an element in A. So now, my X is in here. So that's a true statement. X is in A is a true statement. Then X is in A or X is in B. Is this a correct statement logically? From here to here. Is this logically correct? Is this logically correct?
Yes,
Because?
because of the or statement. So you can, because we're looking at A
Right.
and we want to prove A. So that makes, if we prove that A is in A union B, then there's no reason to prove B.
No. Okay. This
We're
is
assuming A is already true. So
right.
the or statement, we could just focus on what's important.
Absolutely correct. We're assuming this is true. If this is true, this will be true, because the or statement is true if one of them is true. Because we know that this is true. I'm assuming X is in A is true, therefore this is a true statement. So my logic from here to here works, because that's the or tells me the or is true if one of them is true, but I'm assuming X in A, so my or is true. Then X is in A or in B, hence X is in A union B by definition of union. Okay, so now this is becoming actually, oh, that's okay. Okay, this is really becoming a fact that you can use. A is always a subset of A union anything else. I don't care what it is, anything else. Right? Okay. Now let us prove the following. Okay, do we have 15 minutes? You want to prove something? The property, prove the following. And I want to take in another piece of paper. Before that, actually, what does it mean to say A? I talked about A is a subset of B. What does it mean to say that A equal to B? So equality of set. Okay. What does it mean A equal to B? It means everything in A is in B. And everything in B is in A. So A equal to B is equivalent to say that A is a subset of B and B is a subset of A. So A is equal to B, it means that everything in here is in here and everything in B is in A. So to prove two sets are equal, we need to show two things. We need to show that everything in A is in B, so we have to show that. And we have to show that B is a subset of A. So to show equalities between set, we have really actually to do a little bit more work. We have to show two inequalities, quote unquote. All right, so with this being said, let me prove the following. Are we going to do it together? The distributivity properties of set. Distributivity property of set. There are two properties. We're going to show one today. Okay, and I'm going to take the easiest one. I usually forget which one the easiest. So let us prove that. So A intersect B union C is equal to A intersect B. Now we did that at the beginning using the Venn diagram. Now we're going to prove it mathematically. Equal that. Okay, so we have to show that this set is equal to this set. So I have this first set here. I want to show it equal to that. Okay, and we're going to prove it. Since it's an equality, it means I need to prove two things. I have to prove that this is in here and this is in here. So let us start by the first one. So first we're going to show that this is subset of A intersect B union A intersect C. And then I go the other way around. All right. Okay. Now I need your help. I will start to put you on the right path, but as I am moving on, I really need your help. So how we prove this? The idea is the same. We start with an element in the first set, and logically, I have to convince you, if it is in here, it has to be in here. So our first word is let X be in A intersect B union C. And then you're going to do stuff. And then here, by erase, we should end up hence X is in here. So this is really, that's really what I want to get. So that's really, I will never lose track. That's really what I'm going to say, proof. It's like a direct proof. That's my goal, to convince you that this X is in here. All right, so how are we going to prove that? We follow our nose and try to understand verbatim what this means. Let X be in A intersect C. What does it mean? So it means that, and this is I keep my eye here, never forget that. It means that X is in A and X is in B union C. This is by definition of intersection. Okay? All right. What does this mean? It means, where is my X? It is in A. Whatever this X is, it means it is in here, and it's in B union C. That's what it means. But X is in A is in A. That's not a big deal. What does it mean to be in B union C? It means that my X is in A, and my X is in B or in C. And here I use the definition of union. All right, so where is my X? Where is my X? I want your help now. So that's what I need to get. So what do I know about my X now? I know it's in A because there's an and in here. So I already know it is in A, that's for sure. But where is my X also?
So you look at both the cases where X is in A and X is in B, or you look at the case where X is in
Absolutely.
A and X
I
is
have
in
to
C,
consider
which
two
is
cases.
what we were
Exactly.
looking for.
Yes, I have two cases. Why I have two cases? Because I know it's in A. That's guaranteed. That's true because there's an and. But this is a node here. It means I don't know where it is. It's either here or here. It could be in both. I don't really care about that, but I know that at least it's in here or it is in one of them. So two cases are in. So we have to consider two cases. As you realize, we analyze logically the situation. Two cases. Case one, X is in A and X is in B. Remember, that's where I'm heading. If you lose track of that, you lose track of the problem. And case two, X is in A and X is in C. So it's either here or here. And I have to prove, regardless where it lands, it's going to end up in here. Okay, so now I have to convince you that whether it's in case one or in case two, my X will have to be in that. So now, if it's in A and B, in case one, it means that it's in A intersect B. Is this a true statement? If it's in A and in B, then it have to be in A intersect B. That's use definition of intersection. So hence, if it's in A intersect B, then it is in A intersect B union A intersect C. Is this true? If it's in A intersect B, does it mean it's in A intersect B union A intersect C? Come on, guys, yes or no? You're not answering me, it means you don't know the answer. If it's in A intersect B, so assume X is in A and in B, then it has to be in A intersect B because there is an and. But if it's in A intersect B, it has to be in A intersect B union anything. Now the anything I picked is that because that's where I'm heading. So in the first case, X is in A intersect B union A intersect C. Now in the second case, I repeat myself. If X is in A and in C, it means X has to be in A intersect C. That's the definition of intersection. Hence, X has to be in A intersect C union A intersect B. Why I am doing this? Because I have to convince you that whether my X land in A and B, it end up here, or if it land in A and C, it will end up here. So now in both cases, my X is in here. Okay, so I have my first inclusion. So I started with an arbitrary element in here. And I show that if I take any element in here, this element end up in this union. And I can flip those around because like C union D is like D union C. So those could be flipped around, but keeping in track of the parentheses, which are important. So that's my first inclusion. So it's a little bit abstract, but it's not really very hard. Okay. All right, now let's do the other one. The other inclusion. Okay. And this one, I think you should be able to help me more. So, sorry. So the other one is you want to show that A intersect B union A intersect C is a subset of A intersect B union C. Because I need equality, so now we're going to start that. All right. So I want to prove this. I pick any element in here. I have to show that this element is here. All right. So what should be the first thing to write? Go ahead. Or I start calling names. I mean, not calling names, asking you to tell me. So what should be my first sentence? And where should I head? So what should I write here? Let what? Rachel? Rachel, are you with me?
Yes, I'm here.
Okay, tell me what to write first sentence. Where should I start? I should start with an element in here. Any element. And I have to convince you that it is, if it is in here, it has to be here. Okay, so if this is true, then this will have to be true. All right, let's analyze it. What does it mean in A intersect B union A intersect C? What does this mean? We have a union in here. What does it mean? What?
Wouldn't it be,
I'm listening.
wouldn't it be A union B? No, X is in A union B, or X is in A union C.
A intersect, yes. Or,
Oh, A intersect. Okay.
right, that's fine. But you're right. Or A intersect B. Then, by definition of union. I know I always stay here. I know I have to keep going where I'm heading. Now, what does this mean? So where is my X? Either here, in A intersect B, or in here. I don't know, could be here or here. So whenever you have this or, it's gonna always, you or in a way give cases. So I have to take two cases because I don't know where my X is. So I have to show you if X is in A intersect B, then it has to be here. Then I have to show if it's in A intersect C, then it has to be here. So the or tells me, since I don't know exactly where X is, I have to show that regardless where X land, it has to, at the end, convince you that it should be in here. So I'm going to take here two cases. Okay. Suppose X is case 1, X in A intersect B. And then I have to show you it is in here. And case 2, X in A intersect C. So let me stay with case 1. So assume X in A intersect B. It means I want to show you that it's in A intersect B union C. Does it make sense? So if it's A intersect B, does it make sense it's an A intersect a larger set? Okay. All right. Let's see how to prove. Let X be intersect B. Then X is in A and X is in B. Okay. Now I have to show you that it is in A and in B union C. How can I get you there?
Since the X in B So then X in B or X in C.
Absolutely correct. If it's in B, it's in A. So I have it here. I want to show it's in here. But if it's in B, then it has to be in B union C, because if it's X equal B, it means it's in B or in C. So in particular, it is in B union C. So if X is in A and in B, it is in A. And of course, it's in B union C because it's already in B. Hence, it is in A intersect B union C. That's right. That's really the argument we're making. So then X is in A and X is in B. But if X is in B, then X should be in B union a larger set, whatever this larger set, because as your classmate, as there is the or in question, or you can say because B itself is inside B union C. B is inside the larger one. So if it's in B, it has to be in B union C. So I start with an X and intersect B, means X is in A and X is in B. But if X is in B, then X should be in B union C. So now we X, so X now is in A and X is in B union C. Hence X is in A intersect B union C. So in the first case, we showed that if X is in this piece, then it is also in there. Case 2 will be verbatim the same. Case 2. So suppose X is in A intersect C. What time's up? Then X is in A and X is in C. But if X is in C, now I'm repeating myself, but instead of B, then X is in B union C because C is inside B union C. If something is in C, it has to be in union C. So now I have X in A and in B union C. So my X is in A intersect B union C. So whether I take case 1 or case 2, so in both cases, X is in A intersect B union C. So A intersect B union A intersect C is a subset of A intersect B union C. Okay, and for the proof. All right. Time is up, of course. Next time we will spend the whole hour working on those problems, but I really want you to go over what we did today. So it will become a little bit easier next time. So just spend like a little bit of time yourself and take up the problems, the problems I did, and work them out so you can start internalizing this process of proving working with sets, which is very important in math, right? And homework 6 is already on Bright Space for those who like to start. All right, nice to have you guys back, and see you Wednesday. Okay, any questions?
See you.
Okay, bye-bye, guys.